guys, now our group will present about computational fluid dynamics. So this is our group members, which is Afham Shaza and Roberto Dawia, and I am a group leader. So next is Iqbal Shabil and Nazran Adani. I will present about the introduction of CFD. What is CFD? CFD is a computational fluid dynamic. It is a technique that uses computer to stimulate and study how fluid, liquid and gas behave under the different conditions. It provides a way to visualize and analyze fluid flow without needing physical experiment. So, the application is aerospace, which is designing airplanes or rockets, and others is environmental, which is modeling weather patterns or pollution dispersion. So next, I will explain two theoretical equations that we use in our assignment, which is Navier-Stokes equation and Prandtl-Blasius equation. So first, I will start with the Navier-Stokes. First, Navier-Stokes equation is the set of equations that relate to velocity, pressure, temperature, and density of a flowing fluid. So the function of this equation is to describe the fluid motion, predicting the fluid behavior, and application in engineering and science. So next is Prandtl-Blasius equation. So the equation is to solve the boundary layer flow problem for steady, incompressible, two-dimensional flow, illustrating the change in velocity from zero to free stream outside the boundary layer. So the function of the equation is to find the how velocity change across the boundary layer, to find the boundary layer thickness and drag force on the surface. Our objective for the assignment is to examine the influence of airflow transition from laminar to turbulent under the different velocity condition. Next is to analyze airflow patterns for various airflow velocity across the object dimension. And lastly is we can simulate and visualize streamlines to observe flow behavior, identify separation zones, and understand recirculation patterns.
First, we need to open the workbench and choose the fluid. Save this file in this assignment. So we're going to open geometry and pick design modular geometry. But it takes some time to boot up. Upon opening the design modular, into sketching and presetting, the grid must be on. The unit facing is decide to set to 0.1, while minus that maybe is 10. You see the loops there, and when you start to sketch, choose rectangle, plot it, okay, to dimension, measure this as assigned by the lecturers. The vertical is 1 meter, while the horizontal is 0.5. For this, you start modeling, sketch, and this surface from sketches, apply and generate this. You can see here, that becomes a surface and we're going to save this. Okay, close this, that, and go to mesh. Here we will continue with mesh. First we need to open face meshing, insert face meshing, assign surface, to go to the design axis, and apply. We need to insert another sizing, select the edge, pick the top and the bottom mesh, and apply. Element size is changed to the number of division, the number of division is 50. Capture curvature is no, so we can behavior, we can change it to height. That's all for the top and the bottom line. The quick sizing and choose the left side. The left side would be the size is changed to the number of division, which is 60. And the capture curvature is no, in order to change the behavior to soft and to high. Bias type would be the first dotted line, and the bias weight is 70. Okay, assign this. I'm gonna insert another sizing again for the right side of it, apply it. And the size is changed to number of division, the number of division is 60. And the capture curvature is no, change this to high. So bias type is the first dotted line, bias weight is 70, and the reverse bias is choose, since it's a free stream velocity, choose this and apply it. So we get to mesh, we can generate it. See, it's a straight line here. Okay, after that we can assign name, pick face, select the surface and create name selection. This will be our airflow. Okay. This side will be far field pressure. Okay. This will be our inlet. this will be our outlet, and this will be our plate at the bottom of the mesh. Okay, check the name, is there. We can save this project. For saving, we can close it and update this.
After mesh, we do setup. Click setup. For solver option, we choose double position, and for solver processes, we go for 4. It depends on our laptop. So click start. So first of all, we must check this diagram. So click check. After it appear done, we go to model. We want to check this diagram because we want to know that this diagram have error or not. So after that, we go for model. Click model and go to viscose. Viscose. And we choose lamina. Click OK. After that, we go to material. Click material. Click fluid. Click air. This is density and viscosity of air. So after that, we go for boundary condition. Click boundary condition. Click for field pressure. Click for field pressure and change to symmetry. And apply. Close. After that, we go to inlet. Click inlet and change 0 to 1.5 depend on your question that given by Dr. Shukri. And click apply. Okay, apply. After that, close. After that, we go to method. Method. Choose simple because it make more precise. So go to monitor. Click residual, enter 3 because it can be more accurate and precise. So click OK. Okay, we click initialization. So choose standard, compute from inlet, and initialize. And we can move to run calculation. Don't forget, we must change number of iteration to 1 million, guys. Okay, 1 million. Okay, and calculate. So, this is continuity, this is x velocity, and this is y velocity. So this is our graph. After we do some graph, we go to graphic. We click contour. We change to velocity because we want to find velocity, right? Save display, and boom. This is our contour. So the red is a free stream velocity. Meanwhile, the other color is close to the plane. So after contour, we go for vector. Okay, vector, guys. Click vector, save display. So this is a vector, okay, velocity vector. Other name is velocity profile, okay. Take note, okay. After finish the setup for velocity 1.5, we need to do same method for velocity 2.0, okay. So save the project and done. We go for result. Stay tuned. Okay. After we finish the setup, we have done geometry, mesh, setup, and solution. And we have another one. Is result. So click result. So make sure, first of all, we make sure we add z axis. So we do add z axis. We go to contour and click OK. We will change the location for field pressure to the symmetry. We change the number of contour to 50. So then we go to velocity to change. This is our pressure diagram. This is our velocity vector. So after that, we go to chart. Change the x-axis to velocity and y-axis to 1. So the data series structure is missing. So what we gonna do? We need to insert one more line. So first, click insert, go to location, click OK. So our x-axis is x 0.5, 2.205. Y-axis is y coordinate is 0, change to 1, 0, and 0. Sample, we go for 100. And click apply. After that, we go to chart, click series, go for rotation, click minus, and click apply. So this is our velocity graph. So this is our control. So I want to explain about this diagram. First of all, the color gradient. The color bar on the left represent the velocity magnitude range from 0 to approximately 1.04. Each color corresponds to a velocity value with a warmer color, red and orange, indicating higher velocity, and cooler color, blue, green, and indicating lower velocity. For the contour, the contour show area of constant velocity, providing insight into how the velocity varies spatially across the domain. Meanwhile, the domain, the rectangle domain suggests this might represent a simulation of fluid flow, possibly through a channel or around an object. For velocity distribution, from the plot, the red region indicates a zone of maximum velocity near the center of where the flow might be unobstructed. The blue region present near the boundaries. That's all for me, and I will pass to my friend Dani.
So moving on to effect of different airflow, velocity as a profile of the boundary layer. So we have two velocity profile here, which is airflow velocities is 1.5 meter per second and 2 meter per second. As you can see in the graph, the velocity profile gradient for 1.5 meter per second is much more gentle, leading to thicker boundary layer. While the 2 meter per second, the gradient is much more steeper, leading to thinner boundary layer. For the 1.5, the boundary layer developed slowly and its is relatively large, while boundary layer developed rapidly, but it's thinner due to stronger velocity gradient. As we can see here, at low air velocities, the boundary layer is thicker with greater velocity profile. This flow tends to remain laminar. While the 2 meter per second is high, so the boundary layer is thinner. With a steeper velocity profile, this flow is more likely to transition to turbulence. Okay, that's all from me. Moving on.
First of all, to compare the result of CFD simulation with theory. By using the Microsoft Excel, we can find the Y value, or as we know as boundary layer thickness, and the value of initial velocity. Value of eta and f prime was referred at the table Blacher's boundary layer solution. Find the value of y and initial velocity u by using this formula. We can compare the result of theoretical with the simulation by insert the data into the ANSYS software. So we can see the difference of the boundary layer between experimental and theoretical. We do both of the velocity to compare. We can see the blue line is theoretical boundary layer and the red line is experimental boundary layer. These are the difference of using Navier-Stokes solution and Blacher solution. But we can do the comparison by using the formula of this. First, we need to find our Reynolds numbers, and the calculation shows that the Reynolds number was in the range of laminar for both velocity 1.5 meter per second and 2 meter per second. After that, we can find the boundary layer thickness for theoretical and experimental, and we can see that have difference between the effect of airflow velocities on the profile of the boundary layer. For velocity profile, when the speed of airflow low, the boundary layer was smooth, or we call laminar flow. But when the speed of airflow high, the boundary layer thickness become turbulent and cause flattens out the surface. For boundary layer thickness, when the speed was low, the boundary layer become thicker because of allowing the viscosity to spread more. When the airflow high, it's reduced the viscosity and the boundary layer become thinner. But did you know why this happened? This happened because low speed was resulting in a thicker boundary layer with the noticeable viscosity, and high speed caused the flow become turbulent and keep the boundary layer thin.
That's all from us. Thank you.